before I was cut off in the previous video, we were discussing this function. And we've established its shape to be this. And now, we know that on this function, a1 squared is equal to 4a2, which means we will have repeated roots. But look, it also means that if we are above this function, a1 squared will be bigger than 4a2, which means we will have distinct roots. And finally, if we are below this function, over here, it means that we will have complex roots because a1 squared is lower than 4a2. So now that we have established when will we have what types of roots, we can discuss when will we have convergence and divergence. And let's start with case number 1. So what if a1 squared is bigger than 4a2? So then we have distinct roots. In our case, those distinct roots will be b1, b2 equal to gamma 1 plus alpha plus minus square root of delta gamma square 1 plus alpha square minus 4 alpha gamma. Of course, divided by 2. Now, our job is to establish when, under which restrictions on those two parameters, we will have convergence. And convergence will take place if and only if both of those roots will be somewhere between -1 and 1. Okay, but let's remember a couple things. First, b1 plus b2 is always equal to negative a1. Negative a1 is equal to alpha, gamma, times 1 plus alpha, which is clearly a positive number, right? This is positive, this is positive. We also know that b1 times b2 is equal to a2, which is equal to alpha gamma, which is clearly a positive number. And look, what does this, both of those things imply? If sum of two numbers is positive and at the same time product of two numbers is positive, it means that both of these numbers must be positive. So no oscillation over here, and we only need to consider when both of those roots are below, between 0 and 1, or when at least one of them is above 1, right, or equal to 1. Now, but let's consider one more case. Look, what if I multiply 1 minus b1 by 1 minus b2? What will I get out of it? Well, I will get 1 minus b1 plus b2, right? And plus b1 times b2, which gives me 1 minus, multiplying it out, gamma plus alpha gamma minus alpha gamma. Those two cancel each other out. We've got 1 minus gamma, which is definitely between 0 and 1. Okay, so look, knowing all these things, we can go and check which values of b1 and b2 here are permitted. And let's go step by step. Look, if 0, if b, which b2, if 0 is lower than b2, which is lower than b1, which is lower than 1, of course we remember that b2 is always lower because we subtract a positive number. Now, when will this happen? Look, if they are both between 0 and 1, then we will get number between 0 and 1. But what is more, we can be sure that this can happen if and only if alpha times gamma is smaller than 1. Okay, so now let's consider another case. What if we've got 0, so one of the roots is between 0 and 1, and another one is above 1. Well, what will happen with this expression? Look, in this case, what do we get here? This one will be negative. This one will be positive. The product will be negative, which is impossible under the assumptions we have undertaken. So we are disregarding this case. Okay, now what if we've got finally the case when at least one of them is equal to 1. Look, if B, well, in this case, if either B1 is equal to 1 or B2 would be equal to 1, of course we do not need to consider both of these cases. We can just consider B2, and because then B1 would be bigger, which again is impossible. Look, this expression here would turn into 0, right? Again, impossible, not permitted. We can exclude this possibility as well. So none of them can be equal to 1. Okay, so what other possibilities remain here? Well, finally, we can have a case that both of them are bigger than 1. Well, that is kind of unnecessary. And look, this can happen if and only if, well, this condition is then cannot be overruled. We still can have a case where here we get two negative numbers between 0 and 1, and as a result we obtain a number between 0 and 1. But in this case, for sure, we will have alpha times gamma, which is bigger than 1. And look, this creates for us a line that will be distinguishing the two cases. Because look, we see that if alpha times gamma is lower than 1, we will have convergence. On the other hand, if alpha times gamma is bigger than 1, we will have divergence. Okay. So now let's go to case number 2. In case number 2, we have repeated roots, so a1 squared equals to 4a2, and then we've got b equal to gamma 1 plus alpha over 2. Well, b. Now, right away, we can see from that this must be positive. Now, it's impossible under assumptions, we've got here that this is negative. Again, now let's see, what if we take b squared? Look, b squared but A2 for A1, this is nothing more than A1 squared, right? So I can replace it by 4A2. Well, we clearly know, again, that this number must be positive. But look, this, if those two numbers are identical, and what we get over here is that, well, we know that their sum is positive because this is their sum, and if we multiply it, it will be a positive number. We have two positive numbers, but because they are identical, so if we in order to multiply two identical positive numbers and to get positive number between 0 and 1, this number must be between 0 and 1. So b between 0 and 1 will be happening if and only if this is lower than 1. b equal to 1 will happen only if alpha gamma will be equal to 1. And finally, b will be bigger than 1 if alpha gamma will be bigger than 1. And look, actually we arrived at exactly the same conclusion. Convergence, if alpha and gamma, alpha times gamma below 1, divergence, alpha times gamma above 1. Okay, so finally we need to just analyze case number 3. So the case of complex roots. A1 squared is lower than 4A2. And look, in case of complex roots, the situation is easier because all we have to establish is R. R is square root of A2. And square root of A2 is equal to alpha times gamma. So look, again, we will obtain exactly the same cases. When alpha times gamma bigger than 1, we will have divergence. Lower than 1, convergence. That there is one more thing. Look, here can alpha times gamma can b be equal to 1? Well, as it happens to be, it cannot. Why? Because look, if b is equal to 1, we've got 1 equals to alpha 1 plus gamma over 2. So, this is correct. Then we've got that 2 is equal to gamma plus gamma alpha, which if it would be equal to 1, we would have gamma equal to 1, which again is the violation of our assumptions. So look, in this case we can have only convergence or divergence. In the case number 3, we can have convergence, divergence, and non-convergence. Non-convergence happens if we have complex roots and alpha times gamma are equal to exactly 1. Okay, so now, we said a lot, but can we put all of it together somehow? Well, we can, and we do it using the graph, and actually we will use the same graph we used before, but now we can provide it with one additional line. Look, our condition was alpha times gamma is equal to 1, right? If I divide both sides by alpha, I get this. And now look, if I am above this line, it means I will have divergence, right? Because okay, look, let's start over here, right? If I am if alpha times gamma is lower than 1 and all of them are positive, if I divide both sides by alpha, then if 1 over alpha is bigger than gamma, is bigger than gamma, I have convergence. So if I have oh my gosh, sorry. If I am above this line, it means that we have divergence. Below this line, we have convergence. Okay, so let's put it all on the graph. Here we have alpha, here we have gamma. And let's start with the line we already had. This is the line. It has maximum at 1. But of course 1, 0 are out of the scope of interest. And look, another line, this is gamma equals 1 over alpha. So this is like y equals 1 over x. This is just a hyperbola that looks like this. Okay, and now look, what do we see? We remember that if we are above this line, this line means repeated roots. Now, if we are over here, let's just say here, okay, let's do it like this. These are distinct roots, and these are complex roots. Now, let's just say that a purple color will denote convergence. So, we will have convergence if we are below this line. And look, what do we see? That we can actually have convergence under distinct, repeated, and complex roots, as long as the value of accelerator is not so big. Look, this is actually the decisive factor. Look, at the beginning we see that basically all over here, if we are for any value, acceptable value of multiplier, right up to 1, we will always have all the possible cases where accelerator, so when accelerator is below 1, all the cases where we will have convergence. But then, look, as accelerator gets bigger, the value of the multiplier must get lower in order to compensate for it. And look, again, what we establish over here, that for majority of acceptable values over here, the model has complex roots and is dynamically stable. We would say that this type of solution is what produces the business cycles. It's the pattern when we observe the interaction between multiplier, so how much people, so marginal propensity to consume, how much people are spending, and how sensitive are investment decisions of companies to expenditures done by customers. And look, of course, above this line over here we have unstable models, which again can happen for all three cases, for complex roots, because remember, here we have also complex roots, for distinct roots and for repeated roots. But look, I think two things are the most important to remember from this model. That the entire idea of convergence comes here from the fact that if we, for all acceptable values of multiplier, of course, the bigger is the accelerator, the lower needs to be value, not multiplier, MPC, the lower needs to be value MPC to compensate for it. And the second thing is, look, the majority of possible cases over here is in the stable part, and actually it's in a complex convergent part. So this is how we can, and this model actually shows us how can we get business cycle fluctuations even from a very simple Keynesian model. Okay, thank you for your attention. Next week we are going to go back to Phillips curve model, but now we're going to do it in a way that is easier to estimate econometrically, so in terms of difference equations. Thank you for your attention.